Anyway, welcome Bradley and Ralph and Caesar and Victor and Jacob. Thanks for coming. Actually, this is our last day for a while. So we won't come back again for another week. So just to remind you, Friday and Monday are holidays and we take them seriously. So there's no class, no extra assignments or anything like that. The next homework assignment will be due a week from today, just to let you know. So kind of calendar wise, we're in that big long weekend coming up. So just let you know. And then we'll get back and then there's no more holidays again until late May, I think. We do have the 1 week vacation of spring break, but let me share my desktop. And talk about the plan today. So as always, I will start out with any questions you might have, and hopefully I can answer them. And then after that, a lot of what we're doing, we've kind of already done before, but we're kind of putting things together in a slightly different way, a little more abstract. So if it sounds like we already did this, why is he talking about it again? I just kind of go through the book as the way I go. And the book's pretty good in terms of, making sure it drives down all the things that you need to know. So we'll talk about the kernel and image of a linear transformation. Then we'll get into one-to-one linear transformations and the kernel. Then we'll talk about the dimension of the kernel and the image. We'll look at relationships between the two. And then we'll get into linear transformations and bases. So again, a linear transformation just does something to the vector space. But if you have different bases, you visualize it differently, even though the linear transformation is doing the same thing. And we'll talk about that. And then we'll talk about what does it mean to be coordinates of a point. And that sounds like, you learned that in whatever, 5th grade or 6th grade or something. Maybe 7th grade, but we're going to have a much more abstract way of thinking about coordinates of a point, because depending on your basis, the coordinates will be different. And then we'll look at changing coordinates and linear transformations. And then finally, we'll get into matrices of linear transformation when you're looking at that linear transformation with a non-standard basis. So you do kind of like a combo of changing the basis and doing the linear transformation. What might happen, or maybe you're just going to keep the same basis, but it won't be the standard basis, and you have the linear transformation, and you want to write down its matrix. And that's the plan for today. So it's kind of an abstract day, no applications, but we'll get there with applications. It's interesting, the main applications come up after we leave this RN stuff and go into the general. So for now, we're going to RN, which means all the definitions, and then we'll do applications. So that is the plan for today. And I can ask you, are there any questions?
Yeah, could we go over 5.6?
Number 5 was first on 5.6. Okay, so let me go there. Yeah, you know how I do it. Fastest person in gets their question answered, but I might have time for a couple. So 5.6, let me go find it. Number 5, just a second. Okay, so here's 5.6, number 5. And it says, let V and W be subspaces of Rn and Rm respectively. And let T be a linear transformation from V to W. Show that if T is on to W, and if V1 through VR is a basis for V, then the span of TV1, comma, dot, 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 comma, dot, TVR is equal to W. So that's the one you want, right? Okay, so the key on problems like this, and kind of all these problems, is you got to look at the words. And I like to write down what my goal is. Because my feeling is if you don't know where you're trying to get to, good luck trying to get there. Do you agree?
Definitely.
Yeah, so sometimes it's good to know what your goal is. And your goal is to show the span of TV1 through TVR is equal to W. Is that clear? Because that's after the word then. Any questions on that? Okay, so in particular, what does it mean? What does it mean for the span of TV1 through TVR to be equal to W? Okay, and that is that any vector in W can be written as a linear combination of vectors in T, V1, and through TVR. So another way of saying that is that for every W in W, so every lowercase vector W in the vector space W, capital W, there exists a linear combination. So linear combinations now, you got to remember what they are and how they can be written. And they're written as C1. Let's try one more time. There we go. C1 times TV1, because the first vector is TV1, plus dot, 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 plus CR TVR. Oops. Such that that is equal to W. Any questions on the goal? Any questions that that's what we're trying to show? Okay, so now that we know what our goal is, let's see what we're given and we can turn it into things that look like this. Okay, so we are given T is linear transformation. We're given that T is on to W, okay? So if T is on to W, what does that mean? Who remembers what it means to be onto?
It means for every output that there exists an input that corresponds to it.
Right, but in symbols. So for every W, so not quite output, but for every element of the range space in capital W, there exists some vector V in capital V. That's that. What? And by the way, it does not mean that the range is RM actually. Because W is a subspace of RM. So you could think of maybe W is, let's say RM, let's say we're looking at R3 and W might be a plane in R3. So it doesn't mean that the range of V is all of R3. It means that the range of V is all of W, which is that plane that sits in R3. Does that make sense? Any questions on that? Yeah, so we can't say the range is RM. We can say the range is W, which means that for every W in W, there exists a V in V such that, and such that what?
T of V equals W.
Yeah, T of V equals W. Any questions? Any questions on just what that means? All I did is wrote down the definition, basically. Okay, so we're getting there. All right, but V1 through VR is a basis for V. What does it mean for V1 through VR to be a basis? It means two things. What two things?
Linearly independent.
Linear dependent and
Span.
span. Now, for this one, it turns out that span is what we need. Okay, we actually don't even need it to be a basis. We just have to make sure that it spans V. Does that make sense? So it spans V because it's a basis. So since, let's write these out. V1 through VR. So let's insert equation. Yeah. Let's try again. Since V1 through VR is a basis for V, this set spans V. Y'all agree?
Yeah.
So if it spans V, then I can write this little v here, capital V. Got to get this straight. So I know that T of V equals W, right? But I can rewrite V as what?
A linear combination.
A linear combination, so let's write it out. So V is equal to some constant, okay? And I can write that as C1 times V1 plus ... plus CR times VR. Any questions on this statement right here that I'm allowed to do because that's what span means? All right, any idea what I can do next? The hint is it's very simple.
And put that into our T?
Yeah. So I could substitute that in. I have another way of writing V, so let's write it that way in our T. So therefore, and I need an equation. T of V1, C1, V1 plus ... plus CR VR equals W. Almost done. What's the last thing? What haven't I used yet?
Linear transformation.
Right. T is a linear transformation. So what does that mean I can do when I have T of this big summation thing?
That means you can distribute it to every term.
Exactly. And then I'm done. So therefore, since T is a linear transformation, we're done. I'm just going to copy and paste the goal because that's what I can do. It means that I can pull out the C's and split up the pluses. And that's what I wanted. That was my goal. So therefore, we wrote it right. Okay. So the span, so therefore, maybe I should write down the conclusion. The span of, always takes a while to type in. Span of TV1 comma ... comma TVR is equal to W. Because I achieved my goal. Anyone lost on this reasoning? Okay, by the way, I consider this on a scale of 1 to 10 to watch me do this about a 2 or a 3. Does that sound about right? But to do it yourself, it's more like a 9. Sound right?
Yeah.
Yeah, and that's kind of how these proofs are, is that all I did is write down the definitions and put them together. But doing that without being told like what exactly to do is hard. Any questions at all on 5.6.5? Okay, just so we do have time for another one. I think there was a request for 8. I think there was a request for 6 also, but see what they are. So what do you think, 6 or 8?
8.
Yeah.
All right, so good. I heard 2 people. So let me copy and paste 8. Okay, so here's number 8. It says, let's suppose that T is a linear transformation that goes from R3 to R3, given by T of X equals AX, where A is a 3 by 3 matrix. Okay, show that T is an isomorphism if and only if A is invertible. Okay, so if and only if, do you realize that if and only if means we have twice as much work to do? Do you know why?
Because we have to prove that there's no other way to do it.
That's an if and only if. That's a hint. Any other thoughts? Okay, it's important. It means that if no one's saying anything, it means you don't understand what if and only if means. Okay, so let me tell you what if and only if means. If and only if means that you have to start on the left and prove that the right is true if the left is true. And you have to prove that if the left is true, then the right is true. So you have to go backwards and forwards. Any questions on that? And that's what if and only if is. Very different than an if-then statement. So if then, you go forwards only. If and only if, you go backwards and forwards. So let's go ahead and do it because we have both to do. So twice as much work. So always when you have an if and only if, start on the left and try to get to the right. So let T be an isomorphism. Any questions on that so far? Okay. Well, the nice thing is that we had a theorem about isomorphisms, okay? And that is that T is 1 to 1. Do you all agree?
Yes.
Okay, now if it's 1 to 1, we had a theorem about 1 to 1 transformations. And what was that? Do you remember?
The rank of a matrix should be equal to the number of...
No. There's a transformation, not matrices yet. We'll get there with matrices, but right now we're just doing transformation.
T of V equals...
And that implies that V equals W.
Okay, that was a definition, but we had a theorem that made it much nicer.
If T of V equals 0, then
There we go.
V must be 0, right?
That's if T of V is equal to the 0 vector, then V is equal to the 0 vector. Do you remember that theorem? Maybe I'll write down by theorem. Okay, so now let's just use the definition of T now. So therefore, we know that AX equals 0 implies X equals 0. All right, now notice that T, or let's call it A, is what kind of matrix?
A square 3 by 3.
Yeah, it's a square matrix. All right, 4 letters.
TFAE.
Yep, so by TFE, A is invertible. That was one of them, is that the kernel was just 0. Do you remember that? Maybe you don't, but it was one of the long list of things. Okay, so that's one way. Any questions so far? Okay, so next. Now we have to start on the right and end up on the left. Let A be invertible. Okay, well, if A is invertible, then by TFAE, what can we say?
Determinant is 0.
You could definitely say that, but that's not going to help us with trying to show that we have an isomorphism.
Kernel is
1-to-1.
0. Kernel is 0 or
Yeah, so that the kernel is 0. Or what that means is that if AX equals 0, then X equals 0. That's what the kernel equals 0 means. Is that clear? Okay, well, what is that in terms of T now?
1-to-1.
Yep, T is 1-to-1. Any questions on that? But we had a theorem that said that if you're going from Rn to Rn, so by theorem, if T goes from Rn to Rn, and T is 1-to-1, what can we say?
And it's also onto
Yeah, and in particular, in one big word,
isomorphic.
yeah, T is an isomorphism, not ick, but ism. It takes a while to get used to the language. So T is a isomorphism, an isomorphism. Anyone lost on this argument? So this is one of those theorems are helpful. The other one I used definitions. This is definitely one for theorems. Any questions? Again, the big warning is watching me do it is not the same as knowing how to do it yourself. Sounds right? So make sure that you practice these and make sure you can do your own proofs. Okay, and there's plenty. I don't give you every problem in the book, so there's plenty of practice to do proofs. Yeah, and as you saw from the first exam, there are proofs on the exam, just like there are on the regular, on the homework. Okay, and there's also non-proofs. There's just plugging in numbers or matrices stuff, applications. Any questions? Okay, so I think it's time to start the next section. And as I mentioned, there are 2 sections to do today. By the way, if there's 2 sections to do instead of 1, does that mean today's harder or easier? What do you think?
I mean, I think it just depends, but I'm going to go with a little bit easier.
It usually means easier. So if we spend like 2 days on a section, that section's brutal. Okay. If we can fly through 2 sections, that means they were both pretty easy. So I think you won't find today is not one of the most stressful days. Yeah. Maybe you'll think differently, but I doubt it. It's a lot of review. So let me do a little review first. And again, what I do, by the way, I'm not sure if you realize this, is when I write my notes, I just go to the book and then I find all of the definitions and theorems, okay, unless there's some that really don't need to be there, but all the definitions and theorems, and then I try to reword them in a little simpler way. That's my goal. And if you find the book simpler, then, use the books. But I do my best to try and make it a little simpler, and then I can explain them. So just let you know that, I am going through, the order of the book, because I actually like the book's order. I don't know if, do you agree? Do you like the book's order so far?
Yeah, it's not bad.
Yeah. When we first adopted an OER book, the one before this one, it was a nightmare order. Trust me. The first chapter was the most abstract, like all proofs chapter there was. There was no matrices involved. It was brutal. But this one I actually like. It has some issues, and the issues I don't like is that the sections aren't chunked well. But I like the definitions. But there's going to be one thing at the end today that I won't say I don't like the way they did it, but I like my way better, and I made up my way. And if you don't like my way, then you can do it the book's way. But most people that I've been doing this for years now, like my way also. So that'll be later. So here's the first definition of the day. And that is, let's suppose T, going from V to W, is a linear transformation. So I hope you all know what a linear transformation is at this point, because that's what we've been doing for a couple weeks now. Then the kernel of T. Now we've already had the word kernel, but really the word kernel we used for matrices, but now we can use them for linear transformations, and it's not really any different. And the kernel of T is a set of all vectors V in little v, such that T of little v is equal to 0. By the way, is this 0 the number 0?
No, it's the vector 0.
Okay,
vector.
It's a vector, and the vector in what universe?
Our universe.
Which is ours. We got a couple, actually, even in this sentence.
3 dimensions?
Not necessarily 3 dimensions. It could be 100 dimensions, but in particular,
In W.
4.
in W. So notice that this is the 0 in W, not the 0 in V, not a 0 in R3 necessarily. It's a 0 in W because it's T of V. And if you apply T to a vector in V, you end up with a vector in W. And that says that that vector will be the 0 vector in W. Any questions on that? So it's all the vectors in V that get sent to the 0 vector in W. Is that clear? Okay, and that's the kernel. And then the image of T, again, we're thinking of T as a function. So the image of T is where things go. And that is going to be the set of all T of V in W such that V is in V. Okay, a lot of letters, and easy to get confused from all the letters, but you definitely want to get this down. So in particular, the kernel of T is in what vector space?
It's in W.
One more guess.
V.
V.
It's V, because it's a set of all vectors V in V. Do you see?
Mm-hmm.
And there's a condition here about W, but the vectors you're finding are in V. Do you see that?
Yes.
So I'm just trying to make sure, because I know this is confusion for a lot of people. I want to make sure that you don't get confused about that. The kernel of a linear transformation is in the domain, not the range.
Oh.
The image of T, where's that?
That's in W.
That's in W, because it says the set of all vectors T of V in W. So now we're in W. Okay, so the image is in W, the kernel is in V. And it's very important to keep that in mind. So
Now,
you wouldn't even ask the question, is the kernel equals the image? That doesn't matter. It doesn't even make sense because they're in different universes. Is that clear?
So you said the kernel of a, did you say vector space or linear transformation is in V?
Kernel of a linear transformation. There's no such thing as a kernel of a vector space.
Okay, just making sure.
Yeah. Kernel of T, or the kernel of the linear transformation T from V to W, is in the domain. It's in V, whereas the image is in the range, and that's in W. Any questions on that? Okay. And we've already learned how to find them, but maybe I'll do an example. I think it's worth it. Let's suppose T goes from R2 to R1. Make a nice, easy vector space. Let's, where actually, maybe I shouldn't even do R2. Let me go, T goes from, let's go R3 to R2. But we're going to have a V. I think I need to do symbols here. If I could find it. Come on. It's good. In going to W in R2, where V is the vector space spanned by 1, 0, 1 and 0, 1, 0. And W is the vector space spanned by 1, 1. And T of 101 is equal to 0, 2, 0, and T of 0, 1, 0 is equal to 0, -1, 0. Find the kernel and the image. Of T. Any questions on the question? Okay. So notice that, T is a linear transformation, but we're doing the subspace V and the subspace W that it goes from. All right, let's do kernel. How do you find the kernel of T?
You need to find the matrix.
You can find the matrix. Let's do it without the matrix for now. Because we're going to, at the end of today, we'll learn how to find the matrix.
We need to do T of B equals 0.
Yeah, and in particular, V is A. I could call it C1, but it's easier to type A. A times 1 comma 0 comma 1. And I want T of that. Plus B times 0 comma 1 comma 0 is equal to what? If I'm looking for the kernel, what should I set it equal to?
0.
Okay, but be careful about just, it's not the number 0. What is it?
The 0 vector.
0 vector.
Which looks like what?
Like 0.
0, 0.
Yeah, notice that this is a two-dimensional 0. So that's why I want to keep that, you got to keep that in mind, what 0 is it? So it's dangerous to say, oh, it's 0 because that's kernel. But that gets a little complicated. Does that make sense?
And that's because we're going from R3 to R2, correct?
You're going from V to W, and W is an R2.
Okay.
So I want to give a little more info than what you gave. Okay, well, now we just plug in. Okay, well, one thing, T is a linear transformation, right? So that means I can split this up. And I can write this as A times T of 101, but T of 101 is 0. Oh, wait, maybe I made a mistake. Just a minute. R2. No one checked me on this. There we go. Yeah, T of 101 needs to be 0.2. It has to be an R2. Let's see. Sorry, 2. And T of 010 is -1, -1. That's better. So that means that A times 2 plus B times -1 comma -1 is equal to 0 comma 0. So what does that tell us?
That A and B must be 0.
Well, they can be 0, but not must be. Certainly A and B equals 0 works. But the question is, does anything else work?
Yes, A equals 1 and B equals 2.
Yeah.
Yeah, but let me show the steps on that. So we can say 2A minus B. So A doesn't have to be equal, it doesn't have to be 1, 2. It could be lots of different things can happen. Equals 0. Okay, and by the way, the second equation is also 2A minus B equals 0. So I'm not going to bother writing it. Are you okay with that?
Yeah.
So in particular, B is equal to 2A. Hopefully you're all okay with that algebra. So now I'm ready for the basis. And what's going to be the basis? First, how many free variables are there here?
2.
Not quite. 1. A is our free variable. We can let A be whatever we want, and it'll tell us what B is. Do you see that?
Yes.
So what's an easy thing to let A be?
1.
1. Never let A be 0, by the way. That's not okay. Because 0, 0 is never an element of a basis. So a basis is just going to be the single vector where A is equal to 1 and B is 2. And in that case, I'll write it and then I'll do more work. So in that case, it's going to be 1 times 1 comma 0 comma 1 plus 2. Sorry, A is 1, B is 2. 2 times, and then 0, 1, 0. Okay, and that may not look like a single vector, but it is. That's the vector 1, 2, 1. Okay, and this may write basis for the kernel of T. Any questions on that? Okay, now let's do basis for the image of T. Okay, the easiest way to find a basis for the image of T is to realize that it is the image of T is the span of T of a basis. So in particular, it's a span of T of 101 comma T of 010. Any questions on that so far? Okay, so now I just do it. So T of 101 is 2, 2. And T of 010 is -1, -1. Now, what's the span of that set? Or in other words, what's a basis for that, the span of that set? Anyone can tell me? It's nice and easy. Don't need matrices at all. You just look at it. Any ideas? I'm looking at the chat box. I'm listening. I want the span of the set 2, 2 for the first vector, -1, -1 for the second. I want a basis for that span.
It's -1, -1.
Yeah. Okay. And the reason why you could just see that immediately, and maybe I can ask you, what did you see immediately? What did you notice?
Linearly dependent.
Yeah, they're linearly dependent because they're multiples of each other. Okay. So when you only have two vectors, it's really easy. Don't go into matrices. Just look at them. If they're multiples of each other, then you only need one of them. If they're not multiples of each other, you need both of them. Sound fair?
Why did we choose -1, -1 then?
Instead of 2, 2?
Yeah.
Okay, so here's my question. If you have a vector space, is the basis unique?
Yes.
One more guess.
No.
No. In fact, I could, just for fun, it's also a basis is -123, comma -123. Do you agree that's also a basis?
Yes.
Okay. Now, I mean, that'd be crazy to write those down because why spend all the effort? But I wanted to let you know that there's nothing unique about this basis. I chose this one because Victor said it. And if I ask you guys and someone says a right answer, I'm gonna go with it. Sound good?
Yeah, sounds good.
If you said 2, 2, I'd have said 2, 2. Great. Okay. If you said you need both these vectors, I would have said no, because they're linearly dependent. Okay. And in fact, it's also 1, 1 is a little simpler because you can always multiply or divide by a number, a non-zero number. Any questions on this example? think it was important to have a kernel and image example without having to do matrices. I mean, do you agree that you don't need matrices for this problem?
Yes.
I mean, you could use matrices, but if you understand kernel and image and linear transformations and span and basis, then there's no reason to jump into matrices because it's so easy. And if you don't understand it, you're lost. And you need to work harder and get help until you eventually understand it. Okay, so now some theorems. So I'm gonna do one at a time. So the kernel of T is a subspace of V, and the image of T is a subspace of W. So I've already told you that the kernel of T is in V, and the image of T is in W. What's new here? What word is important?
Subspace.
Subspace. Subspace. So for subspaces, what do you have to what do you have to show? Do you remember?
Contains a zero vector.
Huh? What's that?
It contains a zero vector.
Yep, you have to show it contains a zero vector.
Close over addition and close over multiplication.
Exactly. So there's three things you have to show for subspaces. One is that the zero vector is in it. Two, that if you have two vectors in it and you add them, you're still in it. And three, if you have a multiple of a vector, then it's in it if the vector was in it. But now I'm going to prove this using the all at once way of doing it. It's a little easier here. And do you remember there was a way of doing all three at once? Do you remember?
Yeah.
So let's say U and V be in, let me write proof because that's what I'm doing. Let U and V be in the kernel of T. Then what I need to do is I need to show, so write down goal, because that I think helps. My goal is that AU plus BV is in the kernel of T. You guys remember that? That's how kernels work. Okay, so how do I show something's in the kernel? Very easy.
Set it equal to 0.
Not set it equal to 0, but do something. I have this AU plus BV. What do I do to it?
Take the linear transformation.
Yeah, I take T of AU plus BV, and to show my goal is true, what am I hoping this is equal to? Very easy.
The zero vector?
Zero vector, because we're trying to show it's in the kernel. But T is a linear transformation. So what does that mean I could do?
ATU.
Yeah, I can write that as AT of U plus BT of V. But U is in the kernel of T, and so is V. So what's T of U and what's T of V? What's T of U?
0.
Uh-huh. So it's A times 0 plus B times?
Also 0.
0. And you better all be able to tell me what A times 0 plus B times 0 is.
0.
That's 0. Remember, not the number 0, the vector 0. These are vectors. Any questions on that? Was that an easy proof? Okay, hopefully you thought so. I think I'm going to let you do the second one. The second one's similar. I don't want to waste your time too much unless you really need me to show you for the image. But it's basically the same idea. So that's the theorem, and it's an important theorem. It means that the kernel and image are actually subspaces. So a lot of times you're interested in what other subspaces are there once you have a subspace and a linear transformation, and now we know. Okay, so the next theorem is T is 1 to 1 only if, I should say if and only if, if and only if kernel of T is equal to the 0 vector. We already had this theorem. Do you remember? But I'm kind of, I always like to write down the book's theorems, and I'm not going to prove it because I already proved it once. It's exactly the same theorem. So hopefully you remember this one, that always works. So I'm just kind of going through what the book does. Okay, next one. A lot of theorems today. Let T from V to W be a linear transformation from two subspaces of Rn. Okay, so notice V is in Rn and W is also in Rn. They're same dimensions. Okay, they're subsets of the same dimensional space is what I should say. So that the dimension of V equals M. Okay, then M is equal to the dimension of the kernel of T plus the dimension of the image of T. So I'll let you look at that for a moment because it's a lot of words and symbols. So M is the dimension of the kernel of T plus the dimension of the image of T, where the dimension of V is equal to M. This should look a little familiar. Where have you seen something like this?
Nullity.
Nullity and two big words.
Null space.
No, nullity and
Column space.
Wasn't column space. Because it's a number, not a space. Nullity and rank. Do you remember that? So we already know that so let me write this out. It's a very easy proof. And the proof is consider the matrix A corresponding to V, T. Right? And we've already proven earlier that every linear transformation from R and Rn can be written as a matrix. Well, the dimension of the kernel of T then is called the nullity. Any questions on that? And what about the dimension? Oops, dim. What about the dimension of the image of T? What is that with respect to the matrix?
So with the rank?
That's the rank. Because we've already had these theorems that said that. Do you remember that? What is M in terms of A?
Column space.
Close.
0.
No. Closer than row. So M's a number. It's not a space, right?
The number of pivots.
The number of pivots, in particularly, it is the rank of A, which is the rank of the column space of A. Do you remember that?
TFA.
Or the rank of the row space, whichever one, because they're both the same. So M is the rank of A, and why are we done? Who knows?
Because now we can rewrite it as M equals the dimension of kernel of T plus dimension of image of T, and we just showed that that's true.
Yeah, the dimension of kernel of a matrix, or let's go nullity, of a matrix plus the rank of the matrix is always equal to, let's see. Oh, M is the, sorry, M's not the rank. I already wrote that down. M is the, I apologize for that. M is not the rank, it's the number of columns. It's not the column space, it's the number of columns. So we always know that the nullity plus the rank is equal to the number of columns of A. And that's it. That's the proof. Because we had this already. We already proved this theorem for matrices that the nullity plus the rank is the number of columns. And so it corresponds to the same thing for linear transformations. But there's just different language for the same thing. Any questions on this? Okay, so here's an easy corollary. This is one of those obvious corollaries. I hope you all agree when you read it. Let me space things nicely. Why is that obvious? That the dimension of the kernel of T must be less than or equal to M, and the dimension of the image of T must be less than or equal to M.
It wouldn't even make sense because we'd be in a different dimension.
When you say we would be in, it's not where we are.
The matrix.
Actually, not
the
about
matrix.
Huh?
The linear transformation of T, then?
What about it?
It wouldn't correspond to going from V to W if that weren't the case, right?
No, not quite. It comes from the theorem. It's corollary. Corollary means read the theorem.
Dimension of V equals M.
Yeah, that's not what we need to read, actually. It's this equation. M is a dimension of the kernel plus a dimension of the image. Well, what if the kernel was bigger than M? What would that mean about the image?
It should be negative.
Yeah, and what does it mean for a vector space to have negative dimension?
Nothing.
Exactly. Okay. And same thing if the dimension of the image was not less than or equal to M, if it was bigger than M. Well, that would mean that the dimension of the kernel was negative. You can't have a negative dimension. It doesn't even make any sense. Do you all agree? You can't say I needed a negative number of vectors to be a basis. It's just silly. So this is a corollary that's obvious. Do you all agree? So I'm not even going to write a proof because it's just obvious if you just look at the equation, because you can't have a negative dimension of something. Any questions on this? Okay, we're getting there. Okay, now comes what the book calls a lemma. I'm not quite, kind of lemma. I'm not sure if it's the best word for it, but the book calls it lemma. And it says the following. If T is an isomorphism from V to W, and if V1 through Vn is a basis for V, then T of V1 through T of Vn is a basis for W. So I'll let you read that. This is pretty important. Okay. Why must this be true? So we want to prove this. Any questions on the question? So we can always say let, and then I can copy and paste what's given. Let V1 through Vn be a basis for V. What's our goal, by the way?
To show that T of V1 ... T of Vn is a basis for W.
Good, good. And what do you have to show something's a basis?
It spans W.
And?
It's linearly independent.
Exactly. Those are the two things you have to show it's a basis, except there's a theorem. And it has to do with counting the number of vectors. Okay. T is an isomorphism, right? So what do we know about the dimension?
Should be a
It's square.
Yeah, it's going to have to be square, which means you only have to show one of them. But maybe I'll show both because that may not be so obvious. So let's go 1 to 1 first. How do you show something's 1 to 1?
T of B equals 0 and B must be 0.
Yeah, but yeah, it's probably what you were thinking, but T of C1, so it's C1 T of V1 plus ... Cn T of Vn equals 0. Do you remember that? So it's an equation with some sums. So let's suppose that C1 T of V1 plus ... plus Cn T of Vn equals 0. Okay. Well, what can I do? Okay. So we're given that it's 1 to 1. So I'm going to use, it's not 1 to 1 that I want to show. I want to show it's, I need to show that it is, to show it's a basis, I need to show what 2 things?
It's linearly independent, and then it spans W.
Yeah, so let's start with linear independent is what I meant. So to show it's linear independent, I'd say that, and I want to show that C1 through Cn is equal to 0, right? But what can I do? T is a linear transformation. So what can I do now?
Because
Say that C1 times 0, right?
C1 times 0? No, not quite. It's a linear transformation. So I got to use the linear transformation property.
We could put the C1 and the Cn inside if we wanted to.
And I can bring in the pluses.
Yeah.
So I'm gonna do both of those at once. I mean, I can do one at a time, but that's just a lot of work. So I'm gonna write, since it's a linear transformation, then C1 T, then T of C1 V1 plus ... plus T of, not T, plus Cn Vn equals 0. But we know T is 1 to 1, don't we?
yeah,
So what does that tell us?
at C1 B1 plus ... Cn Bn must be 0.
Good, good. So let's see if it lets me do it. Okay, so we know that's true. I still have the parentheses because it doesn't let me have no parentheses. Let's see, I know. That's better. All right, but since we know that V1 through Vn is a basis for V, what does that tell you about the C's?
They're arbitrary?
Oh no, definitely not arbitrary. That's our whole point.
They are 0.
They're all 0. That's what it means to be a basis, because that means that so a basis, remember, span linear independence, and we know that the V1 through Vn are linear independent, so CI's, so C1 equals C2 equals ... equals Cn equals 0. And we're done for linear dependence. Any questions on that? Anyone lost on that proof? Okay, so now I have to show span. Span is basically the same. And in fact, I think it'll save me if I just copy the whole thing and adjust. So now we want to say let not C1, T1, ... be 0, but now we want to find C1 through Cn such that you'll get any vector in W. Is that clear? So let W be in W. Okay. In fact, I don't think I need all this. Well, what do we know? Actually, I think I don't even want to start there. I want to span it. So we want to show that what? I guess we do want W be in W So we want to show that it spans W. W be in W. So our goal is to find some T1, V1, ... Tn, Vn, such that a linear combination of those is equal to W, right? Any questions on that? But if it's since T is an isomorphism, we know it's onto. So what does that mean?
We know that T of V1 ... T of
Not yet. We're not there yet. No ones and twos anymore. Just onto. There exists.
A vector in B.
Yeah, V in capital V, such that. And Victor, what is it?
Equals W, a vector in W.
T of V equals W. Any questions on that? That's what onto means. Okay. Well, now what we need to do is we need to kind of turn that into span. But here's the idea is that V now, any V can be written as C1 V1 plus ... Cn Vn because V1 through Vn span. So I can say T of C1 V1 through Cn Vn is equal to W. But then finally, what can I do?
Pull the constants out and separate the parentheses as addition. Distribute T basically.
So basically I do the same thing with the kernel, except it's a W now. And that's it, I'm done. Therefore it spans. So that's the proof of that lemma. I thought I'd do these kind of proofs because you need practice. Hopefully watching me will maybe get you to do some practice on your own too. Don't just assume you watch me so you know how to do it. Make sure you do it yourself. Okay. Now a definition, very important. And let me remind you, before I even talk about this definition, when you were in really first year calculus, but also in last quarter, if you had a point in, let's say, XYZ space, was there a unique way of representing that point with coordinates? Think last quarter.
Yeah, we could change coordinates if we wanted to.
Okay, so the answer is no, because you can change coordinates if you wanted to. It's not unique.
Oh, I see.
If I
Okay.
told you I have coordinates of a point 2, half, 1, I have not told you enough to be able to plot it. Do you know why?
We don't know what coordinates we're in.
Right, I might be talking spherical coordinates.
Yeah.
Or maybe I'm talking cylindrical coordinates. Okay, or maybe I'm talking rectangular coordinates like you're used to. But you learned that last quarter, right? Is that there's lots of different ways of writing a vector.
So
Okay,
since there are multiple ways of writing a vector, it's not unique.
Right, it's not unique. Unique means there's only one, right? That's
Yeah.
the definition of unique.
Okay.
Okay, so it turns out, now I'm not going to get into cylindrical and spherical because those aren't linear. Hopefully you know that, because I don't know if you remember, but x is equal to r cosine theta. Do you remember that?
Yeah.
There's nothing linear about r times cosine theta. Do y'all agree? Okay, so in this class, we're only going to do linear stuff. And we're also going to be doing in Rn instead of R3 or R2. So, but it turns out for any basis, we can write down coordinates. So here's the big definition. Let B equal to be a basis, V1 through Vn for Rn, and let little v be a vector in Rn. Then we always know that V can be written as C1 V1 plus dot 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 Cn Vn. That's part of being a basis, right? And that's unique, right? So what we can do is we can take the C's and write them down in kind of point form, C1, C2, dot dot, Cn. Put some parentheses around them. So it's not a vector, it's a point. And this is the coordinate of the point V, or the vector V, with respect to the basis B. Any questions on this definition? Okay, and if I choose a different basis, will I get the same coordinates or will I have different coordinates?
I think it just depends on
Doesn't depend, actually.
then yes.
If it's a different basis, I get different coordinates. So for example, if I use a standard basis, let's say in R2, 1, 0, and 0, 1, then I could look at the coordinates 5, 2. Okay, and you know how to draw that. But I could also look at the kind of a flipped basis, say 0, 1 for the first vector and 1, 0 for the second vector. And then I'm going to flip the numbers. Do you see that? So different bases is going to be different coordinates. Just like if you use polar, you're going to have different numbers, different coordinates than if you use rectangular. So same idea. Any questions in this definition? Okay, so here's a theorem. Let's suppose we have a basis B, V1 through Vn, of Rn. And consider the function that takes a vector to its coordinates. Okay, so the domain of the function are all vectors in Rn, and the range are also vectors, but they're the coordinates of the vector. Any questions on what this function is? Then this function is a linear transformation. Any questions on this idea? Any questions? Okay, so let me do kind of an example, and then I'll show you how to approach it. Okay, so let S be equal to, how about 1, -1? Make it in brackets, curlies, comma, 1, 1. By the way, is this a basis for R2? Yes or no? Should be an easy answer.
Yes.
Yes, yes, because they're linear independent because they're not multiple of each other. There's just two of them. And there's two of them, and that's the number we need. And if they're linear independent and there's two of them, it's a basis. Is that clear? So suppose S is this basis. And let's suppose T, not the transformation T. Maybe I shouldn't use T. How about B for basis equal a different basis? So how about 1, 0. Now let's make, that's too easy. How about 2, 1, 1, 2. Is that a basis for R2?
Yes.
Okay. So yes, that's a basis for R2. All right. So we have different bases for R2. What I want to do is let's suppose that the coordinates of V with respect to S be 3, 4. The question is find the coordinates of S, sorry, not of S, sorry, of V. V respect to S, that's right. Coordinates of V with respect to B. Any questions on the question? Any questions? Do you all understand what I'm asking? Any questions? All right. Any thoughts about how to go about this? And the hint is it's a trick one. There's a tricky way to do it, but it's always the trick you're going to use. Any ideas on that trick to make it easy?
Do matrix multiplication?
There's going to be some matrix multiplication, but what matrix? And that's going to take some work. Okay, so what we're going to do is the following. Is we can think of this as, let's just write S going to B. Okay, it's not quite, we're taking a basis S, sending it to the basis B in a way. Well, the idea is that's too much to do. It's kind of like if you had to drive from here to Kansas, could you do that in a day?
No.
No. When I did that, I stopped over in Denver. Okay. I did drive a long way each day. I did it in 2 days. And Denver was nice and easy. So what I'm going to do is I'm going to start in S and not drive all the way to B. I'm going to go to the easy place first. How about E for easy? Sound good? Okay. And it turns out E also stands for something else. What does E stand for in this class for bases? It's the first letter of what word?
Elementary?
Yep, elementary basis. So what we're going to do is we are going to go from S to E, and then we're going to go from E to B. Any questions on that idea? And let's first go S to E. I want the matrix that takes me from S to E. And the hint is it's very easy. Okay, I say relatively easy, maybe a better word. What is that matrix?
1, -1, -1.
Are you
as
reading rows or columns?
Columns. I was
Column.
reading it as columns.
Yeah.
And then
And
1,
then 1, 1. And we've already talked about that. If you want to get back to the regular elementary basis, that's how you do it. Any questions on that idea? Is that clear? Okay, so I'm halfway there. I'm in Denver, right? Okay, now I have to get from Denver to St. Louis, okay? And if you ever done that drive, it's a boring drive, okay? A lot harder to stay awake than it is to go from here to Denver. So we're gonna do more work. And the idea here is we're gonna go from E to B. What we can't quite do is the following. It's what you'd like to do, but you can't. You can't just say, well, B as 2, 1, 1, 2. What's wrong with that?
Where did E go? That's my thought process.
What do you, where did it go?
Like you said, we would want to write it as E to B is that new matrix, but we still have an original E. Don't we have to multiply?
No, this is just going from E to B. Why is this not going from E to B? This is not the matrix that takes E to B. What's the problem?
Well, in E, there's a negative. I don't see a negative in there.
No, nothing to do with the negative. E doesn't have a negative. E is just a standard basis. You know, your 1, 0 for the first and 0, 1 for the second. Right? Your normal, good old-fashioned XY coordinate system with good tick marks that have length 1. That's E.
It can be that if we want to return to S, it's not the same.
No, not quite. All right, it has to do with the arrow. Going from S to E, the arrow goes in that direction, right? Going from B to E would be this matrix. Do you see that? And we don't want to go from B to E. What do we want to do? We want to go from E to B. So what do I have to do?
The transpose?
Not the transpose. A different superscript.
The inverse?
The inverse. Because I'm going backwards. Backwards is inverse, right? I got to drive backwards. Very hard drive to St. Louis from Denver backwards. Any questions on that? Because if we want to go from E to B, that's going from B to E backwards. And backwards is inverse. That's the definition of inverse, isn't it? Okay, so now we want to put it together. So now we're ready to put everything together. And what do? Well, which do we do first when you're doing this drive from S to B?
Go S to E first.
Right. Now you have to be very, very careful. So I'm going to go S to E. And then we want to go from E to B. But this is where you got to be careful because these are functions and functions get read backwards. So you got to read from right to left and then it works. And then I need to multiply by this 3, 4, right? Any questions on this? Now, I don't think I'm going to waste your time. Do you all know how to do this if I asked you to do this? either by hand or by symbol lab at this point?
Yeah.
You all know how to multiply matrices and find an inverse?
Yeah.
Yeah. So are you okay if I don't actually work this out by hand? Because it'll probably take 10 minutes for me to like type it. Writing it by hand, literally by hand, won't take as long, but hopefully you know how to do that. And the idea is if you want to find the matrix that sends something with coordinates in the basis S to coordinates in the basis B, this is how we do it. You take that something, you multiply by the S matrix, and then you multiply by the B inverse matrix. Okay, and remember, everything's read from right to left. Any questions at all on this?
Is this the same thing as finding a Jacobian?
No, there's no derivatives. Finding a Jacobian was taking partial derivatives.
Mm-hmm.
And remember, this class doesn't even require calculus. I think I told you I had this class before I took calculus because teachers didn't understand math well enough to know what to give me with high school. Okay, any questions on this? But I will tell you, the most important person to me that we've ever had in this college took this class. Who's the most important person ever?
Me?
Yeah, you to you. My daughter. So she was in high school when she took this also, because I was mean. So you could do it. If someone could do it in high school, you can do it now. Any questions on this? Okay, let's go ahead and make it more complicated. Remember, what is this chapter all about? In 2 words?
Linear transformations.
Mm-hmm. So now I want to put in linear transformations. So I showed you if you want to go from one basis to another basis, how do you do that? But what if you also are doing a linear transformation? And maybe you're doing a linear transformation, but you're starting in one funny basis and you're ending in another funny basis. And you want to find the matrix that does that. Any questions on that idea? So to do that, and again, this is not from the book. This is something that I made up because I found it, at least for me, a whole lot easier than the way any book does it. But I draw a picture. So here's my picture, and maybe it'll be confusing to you, but because it's busy. All right, so the first thing is it's a very messy picture, but it's going to help us a lot. So if we have a basis for V and another basis for V, so the first basis I'll call S, the second basis I'll call T. And if we have a basis for W, first one I'll call Q, second one I'll call R. I'm just running out of letters, so I got to pick something. And let's suppose I want to take something in the basis S, and I want to end in the basis R. And I'm given what the linear transformation does from a basis from S and a basis from T, and maybe from Q and from R. Then this particular diagram is going to help me a lot. So let me give you all these letters. So A is a matrix of columns of the basis S. So we found out that if you're going from a basis S to the elementary basis, you just write down the columns. Do you remember that? And similarly, B is a basis of columns of the basis T. So B inverse will take from E to T. C is going to be the matrix of columns of the basis Q. D is going to be the matrix of columns of the basis R. And notice it's a D inverse to go from elementary to R. And then we have F is the matrix of the linear transformation T with respect to the bases S and Q. G is a matrix of the linear transformation T with respect to the standard basis, E and E, just standard bases. And H is a matrix of the linear transformation T with respect to, with linear transformation, I shouldn't use the letter T, should I? L for linear transformation is better. Because I've already used L for a basis. I mean, T for basis. So H is going to be the matrix for linear transformation L with respect to the bases T and R. I'm going to let you stare at this diagram for a moment. Once you get it, it's actually not that hard, but there's a lot of letters. Any questions at all on this diagram? Okay, just to see if you get it, of these matrices, A, B, C, D, F, G, and H, which ones must be square matrices? And which ones don't necessarily have to be square? So which ones have to be square matrices of these 7 matrices?
A, B, C, and D?
Yeah, A, B, C, and D must be square because they are matrices of basis change. And changing a basis is always square because the dimension's the same. Whereas F, G, and H do not have to be square because V might have a different dimension than W. F, G, and H have to be the same as each other, but they don't have to be square. So I just want to make sure that you kind of get the idea here. Okay, so if we wanted to go from the vector space V and we're given the basis S, we want to end up with the vector space V. Oh, sorry, that should be W. You should have asked. Vector space W with the basis R, then we have lots of choices. And the nice thing is what you want to happen is true. And that is, if you wanted to start at this VS and end up with this WR, is there only one way to get there? Arrows are roads, by the way. Or do you have lots of choices to get there?
You have more than one choice.
Yeah, there's a whole lot of choices. So we could do A, B inverse, and then H. So notice, I think I'm going to copy and paste this so that I can write below it. Otherwise, you're not going to be able to see it. That if we take A and then do B inverse, remember, you always read backwards, and then do H. Then that'll be the same as what's another way of getting there. Any thoughts? Because you said there were lots of choices. What's another choice?
H D inverse A.
H D inverse? H and D inverse can't be together, actually. So again, the way we just did is we started here and we went right, and then we went right, and then we went down, and we got to WR. How else can we get there?
If you go down.
And go down, and then?
Right.
And then?
Right.
And right. So those are going to be the same. And that is going to be D inverse CF. You always read backwards. And those will always be equal. Okay, and the proof is by diagram. Not a nice proof? So let's use this. Do an example. So let's go B be the basis. 1, 1, comma 1, comma -1. Oops. Try this again. Do you agree that's a basis for R2? And, oh, just a minute. I lost all that stuff. And let's say C, I'm going to choose different letters because you're not going to be given these letters. C be the basis. Zero, comma 1, comma 1, comma 1, comma 1, comma 0, comma 0, comma 1, comma 0. And hopefully that's a basis, but let me double check. Yeah, that works. And let's suppose T is the linear transformation from R2 to R3 with matrix in the standard bases. And let me draw a matrix. Oh wait, R2 to R3. Sorry about that. And if you're going from R2 to R3, that means there's 3 rows, 2 columns. So it takes a moment to make them happen. So 2 columns, 3 rows, sorry. By the way, is T going to be an invertible matrix?
Yes.
One more guess.
No.
No, it can't be. It's a 3x2 matrix. 3x2 matrices can never be invertible. Is that clear? Yeah, you can never have an invertible matrix from R2 to R3. It can't happen. You can only have an invertible matrix R2 to R2 or R3 to R3. Okay, so that's what our linear transformations matrix is. Find the matrix for T with respect to B and C. Any questions on the question? Any questions on the question? All right, so I'm going to steal this diagram. And I'm going to adjust, do a whole lot of adjustments. First thing, I actually don't need all of it. I only need this amount. And what I'm going to have is, let's change the letters about. So we have a basis B. and the basis E. Then we're going to have the basis C and the basis E. And then, I don't know, let's call it A1 and A2. Should I do it? No, let's give them letters. I haven't used A yet. I've used B and C already. Let's call that D. And F and G are fine. Okay. And V, of course, is R2. But let me do R2. There we go. And W is now R3. Like so. Any questions on this? Let me label this matrix, the 1, 0, 2, 1, negative 1, 0. Which one is that in our diagram?
Did you say 1, 2, negative 1?
This one here, the 1, 0, 2, 1, negative 1, 0. This one here.
It will be the R.
I'm looking for a letter. It's going to be A, G, D, or F.
A.
It's not A. Good try, though. A goes from R2 to R2. That would be a 2 by 2.
It will be
So
D.
G.
It'd be G, because that's under the standard basis. So that's G. Actually, I don't want to change that. I want to change this guy. So that's G, just to get our thing straight. Any questions on that? Okay, and the idea here is what we want to do is we need to go to R2B, and we need to end up at R3C. Is that clear? So to do that, so we need F, right? Well, to get F, you go A, then you go G, and then you go D inverse. Any questions on reading this diagram? So to go down here, you go all the way around. So
Why can't, because of, if the standard basis was different, we could go straight down?
well, the straight down is what we want to do, but we don't know what that matrix is.
Okay.
Yeah, if you were told that matrix, then you do that, but that was the question. What is that matrix? So F is equal to, again, we're going to do A, then G, then D inverse, or D inverse, GA, because remember, you always read backwards. We already know what G is. So we need to find out what A is. Okay, and the rest actually is kind of busy work if you understand it. So A should be a 2 by 2 matrix. Whoops. Do it one more time. That's better. And what is the 2 by 2 matrix A?
1, 1 as columns, 1, 1, and then 1, negative 1.
Good. So that's what A is. Any questions on that? Okay, now we also need D, and then we'll take its inverse. And just to make the typing easier, copy this one, get rid of everything, and add in a column. So D now, will be a 3 by 3. So D will be a 3 by 3 matrix. And unfortunately, we can't see everything on the same screen. It's too much is the problem. We're almost there, by the way, because we're out of time, but I'll just finish and we'll be done. So to get D, I just write these 0, 1, 1, 1, 1, 0, and 0, 1, 0. And I just write those as columns. So 0, 1, 1, 1, 1, 0, I think it was, and 0, 1, 0. Any questions on this construction? Any questions? Okay, and then what you do is you take D inverse times G times A. Symbol Lab's great for that. And you'll get a matrix. Okay, I'm not gonna do it by hand. We're out of time anyway. So what I'm gonna do is I'm going to be done just a second. And wish you a wonderful vacation.